All right. So welcome back. We haven't had a lecture now. It's been 2 weeks since our last lecture. I know, I'm disappointed too. Particularly because the content that we're covering today is where everything starts to get a lot more fun. Today well, when we left off last time, if you remember 2 weeks ago, what we were talking about was the relationship between the input and output in a system, which is ultimately dictated by physical properties. And every one of the systems that we dealt with had some governing properties that ultimately stated whether or not a system was valid. So what we were dealing with was we had, for example, like the electrical equation we had was the current through the source is equal to, I don't know, some function of the capacitor voltage, where the function of the capacitor voltage was potentially a second order differential equation. And this is where basically we left off. Now, for what we're looking at in our systems and controls class is we have input, control, output. And this is ultimately what we're trying to get to, is how do we take the input, modify it, so that we can adjust what the output is going to be. Okay? And this is the sequence really that we're looking at. Well, what we're going to define the control as today is we're going to define control in a much broader sense. So here, the input was equal to some function of the output. What we're looking for is VC is equal to some function of the input. But the issue is we don't really know how these two correlate. But if we did know how these two correlated, and if we did know ultimately what this control was, we could figure out this relationship a lot easier. It would be really nice if we had this kind of formula where we had VC is equal to, I'm going to go ahead and call that G, and we'll go back and explain that, times IS. That'd be awesome. Okay, where all we have to do is take whatever the input is, multiply it by something, and we get the output. This would be a really easy, nice, clean formula. But based on the formulas that we've been dealing with, like for example, if we're talking force is equal to mx double dot plus c x dot plus kx. Now if we're looking at a system like this, and we want to try to write this as some output variable where your output is x is equal to g times f. Well, there's no constant that we could plug in for g to make that happen. That's kind of unfortunate. Okay, so we're going to go ahead and define G as a transfer function. where g is equal to the function x with relation to time divided by f with relation to time. Okay? Where we are not looking at g, I guess this is, yeah. We're not looking at g such that g is a constant. We're not looking at g such that g is a function. Okay? And if we have this, and we can multiply it by whatever function f of t is, we can find what the function x of t is. Okay? This is ultimately what we want. If we could figure that out, then this whole process gets a lot nicer. Because then it's just, then rather than having to friggin' solve the problem every single time or change values and go back in, nope, or solve that problem and plug in different values of f every single time, this is one-stop shop solution. It's over, it's done. Okay, so this transfer function, if it exists, would be a huge benefit to us for many reasons. Okay, let's say we've got a system like a vehicle suspension where you've got your spring, you got your damper, and then you got your spring again. Okay? If you find what the transfer function is for the height x1, then you can find that the transfer function for simultaneously the height x2. Okay? And what it ends up being is that x1 is equal to, let's say that it's a function of h, the height of the roadway, the height of a bump in the roadway. So x1 is equal to g of t times h of t. Both of those are functions. Okay? Well, x2 is also going to be equal to some function not just of x1, but also of h. So x2 ends up being some function, we'll call it h of t, times x1 of t. Because really it's the movement of x1 that changes x2. Well, if we know that x1 of t is equal to g of t h times h of t, and that means that x2 is equal to h of t times g of t times ht, which means we can find the overall movement of the system if we know the two transfer functions that lead to it. Okay, this actually greatly simplifies any system where power transfer occurs. If you're dealing with an electric motor where power is transferred from electricity to rotational motion, and then maybe that electric motor is hooked up to an axle of a vehicle where it then turns into translational motion, you can build your transfer functions from where the energy, where the power leaves the battery, all the way to where the power hits the vehicle. And you can study that transition. And based on how you develop your transfer functions, or how you modify them, control them, whatever, you can adjust the behavior such that the vehicle goes faster for higher power consumption, or the vehicle may not accelerate as much for higher power consumption, but may be able to reach higher speeds. That's just based on the gearing. So having this transfer function allows us to solve more complicated systems because the transfer functions do connect in this way. one input, the input to one system is the output of another system, which means you can solve the output of both systems by using the transfer functions. Okay? So that's just one example. Now, the problem with transfer functions is, again, this is a very complex function. We can figure out the relationship here. We can figure out what it is that the input is as a function of the output. That wasn't hard for us. But flipping that around and figuring out what the relationship between the output and the input is tends to be a lot more challenging. And this is where the brilliant minds who have come before us invented something known as the Laplace Transform. Which, have any of you in here done the Laplace Transform before? 1? 2? I'm sorry. The definition of the Laplace Transform, hold on, grabbing it. I don't have this memorized. Which I guess is my bad. The idea behind a Laplace transform is that we're going to take some function, f of t. This marker's dead. Did that make it? First time ever. We're going to take some function f of t, okay? And what we're going to do to that function is we're going to transform the time scale. We're going to make this not a function of time, but a function of some other variable. It's an arbitrary variable called s. And what we're going to do is we're going to find that by multiplying this function times e to the negative st dt. We'll form the integral from 0 to infinity, and we're going to call that capital F now of s. One thing that Laplace transforms tend to do is when dealing with Laplace transforms, you tend to have lowercase function values, like here lowercase f as a function of time, and use an uppercase f as a function of s. Yes, I did that exactly backward all over here, because everything is a uppercase value function of time. But from here on out in this class, I'm going to try to maintain that consistency. So, this is the definition of the Laplace transform. I don't want to do a lot of those integrals. I got out of calculus, and I mean I know how to do it, but I don't willingly try to go in and like, ooh, I have a new function. I'm going to do an integral. So there is actually a massive inventory of Laplace transform tables available online. There's even one in your textbook. So I'm not requiring you to write these down, but there's just a ton of different Laplace transforms available. Let me go ahead and no, I'll just write some on the board.
Is that e to the negative st or e to the negative 5t?
It's an s. Okay, so I'm just quickly Googling Laplace transform tables, which they're everywhere. I just found a really quick one from lamar.edu. So for example, if f of t equals 1, then f of s is equal to s. That's interesting. Oh, sorry, no. 1 over s. Okay, so that's fun. If f of t is equal to t to the fourth, then f of s is going to be equal to, what are you? 4 factorial. So that's what the exclamation point is. It's not just a really excited 4. Although maybe it is. It's being put in a giant math problem. Divided by s to the 4 plus 1. So this ends up equaling 4 factorial is 4 times 3 times 2 times 1, which is 24, divided by s to the 5th. Which that's a 5, Brendan. Not that you can tell, because my s's do look a lot like 5s. Dang it. Maybe if I do something like this. And you just write my s's like this.
Yeah.
See, there's an S.
That works.
It looks more like a lightning bolt.
I think it looks like that.
Well, I trust Brandon's opinion. So, okay. Now the thing that we've had to deal with a lot in this class has been, what if f of t, for example, over here, is equal to c x dot, where x is some function of time. Now, how do you handle that? Well, the Laplace transform of a derivative, let me find it here. There's actually a specific way of writing it. Oh, where are you? It's in this table somewhere. Right. Is equal to S Fs minus F0. So that is here, if this is a derivative, then the sorry, this would be an x. Let me rewrite this. And that makes f of s, capital F of x, is equal to c times s times x of s minus x at t equals 0. Okay, so do note there is a difference between a capital X here, and that's a lowercase x. What this means is you have to be able to perform the transfer function of x. Now this is kind of gross because the transfer function of this value right here ends up having a giant capital X, also a little lowercase x. Just taking the Laplace transform of it is kind of gross. Why did I introduce this to you? Well, the reason why I'm introducing this to you is because this is a tool that we're going to use to find the transfer function. Oh, where's the eraser? Okay, since the function connecting the input and output is so complex, the Laplace transform was actually created as a way of being able to separate these members algebraically. When we work in the S spectrum rather than in the time spectrum, it allows us to have different mathematical properties. It's much like, I have an analogy I usually use. Can't think of it right now. But it's like, imagine if you were to think of your position everywhere in time. So at certain times, you were at certain places. And then to suddenly switch and say, well, instead of thinking of your position in time, think about your position in space. So that I am at this location, but that is at a certain time. It's kind of like an exact flip of that. That's basically what the time and the S spectrum are. They're flips of each other. They're both correlated, but it's two different ways of looking at the same mathematical equations. So if we're dealing with a transfer function, we're going to go ahead and say that the transfer function in the Laplace transform, we are oftentimes able to get it such that if we were to divide the output by the input, we get the transfer function as long as we do it in the S spectrum. And this is a linear function. What is meant by that is that the Laplace transform allows for us, when we do this right here, when we take the derivative, this is a linear function. This doesn't have a derivative in it anymore. It removes the derivative by taking the Laplace transform. And because we're able to remove the derivative, we are able to make this a linear function. Linear function means we can directly multiply input by transfer function to get output. But it has to be in the S spectrum. Okay, so kind of gross here looking at, this is one of the reasons why, well, thanks for commenting on the video. This is one of the reasons why control systems tend to be a little ugly. Because in order to get our linear transfer function, we have to take the Laplace transform of everything. This week, we're going to be working on building the Laplace transforms. Talk about how to take those, how to make those. Next class on Thursday, we'll give some examples of taking the Laplace transform. But we're not going to do that today. So, any questions over this so far? Do you realize that we're just getting our feet a little bit wet in terminology here? I will say that we're not going to go terribly, horribly in depth into this. I'm not going to make you do Laplace transforms for the rest of the semester. Some people in this class haven't taken differential equations yet. So this isn't something where I'm going to expect you to do extensive differential equations. Now that said, I'm going to have to walk you through how to do these. And that's okay with me. I'm not going to, like I said, we're not going to have any tests over this kind of material. But I do want you to be familiar with how the calculations are performed, because if you were to go on in grad school and do anything with control systems, you would need to understand how these Laplace transforms are done, how to use them in transfer functions. Okay, I'm going to go ahead and end the live stream, and